Hello and welcome to the ninth part in the series of videos aimed at developing retro games in vanilla JavaScript using the canvas element. My name is Anthony, and please join me in my corner of the web where I like to build stuff in the browser using the latest technologies. It feels like a lifetime since the last video, honestly, but I did finally get a well-deserved vacation abroad at the end of September, which meant I wasn't in front of my usual PC. I was, however, getting some sun for what probably will be the last time this year for me, at least living in the UK, as we move into autumn. Although I'm now feeling refreshed and ready to pick up the series again. The general consensus from the last video was that we should finish off the background and UI before moving on to the actual fighting moves. So with that in mind, I think it's wise that we jump straight into the dreaded to-do list once more and pull up the remaining things we should tackle today. Scrolling through the list, there's still a number of items that relate to both the background and the status bar overlay, which we're able to tick off. So in summary, in this video, we'll start by adding the only UI element today, the text along the top of the screen that represents the scores for both the players and the current high score. We'll then move on to the background and look to add the missing various animations. These include the boat animation, along with the characters on it. We'll then move on to the floor and discover how the 3D effect was applied to the original game, which it's so famous for. We'll then look to simulate this within our version of the game, using a transformation effect. Finally, we'll move on to the objects that sit on the floor itself, some of which appear in front of the fighters. So yes, there's still plenty to do in this area, although by the end of this video, we should have a near complete stage that resembles the original version and game. And before we move on, I'd like to quickly thank those who have signed up to my Patreon page. It's got more followers on there than I expected, especially at this early stage. There's still plenty of work to be done there, but if you'd like to get direct access to the code and early access to these videos, or just say thanks and support what I do here, then that would be the place to do it. So thanks again to everyone so far who has taken the time out to support this channel and my work. Okay, enough talk, let's crack on. So where did we leave the code in the last video? Well, if you've been following along, we mainly focused on the UI and background, replacing the static image background we've had since the start of the series with a set of different layers stacked on top of each other to replicate it. We also added a camera to allow us to move our entities in 2D space, which in turn transformed our static background into a scrolling parallax one. Lastly, we started to add the UI elements at the top of the screen to represent the game's details, such as the fighter's health bars and the battle countdown timer. We'll look to continue where we left off in today's video, finishing the remaining components in the status bar before moving on to animating the background elements. And finally, applying the 3D skewing effect on the floor, leaving us in a perfect place to jump right back into the state machines in the next video, where we'll start to tackle the basic attacking moves. But we're getting ahead of ourselves already. Let's start by updating the UI and the scores that appear across the top of the screen. If we take a look at the original game again as reference, there's a couple of things to note. As we mentioned in the last video, the status bar is generally split up into 3 sections, and funnily enough the scores are no different. On each side of the screen we have the individual fighters' scores, and in the middle we have the current high score from the stored table of high scores. We'll talk more about the high score table later in the series when we discuss global states, but for now we'll just use a known default value from the original game. Notice how each section has its own label followed by the actual score value. To allow us to draw these strings and values to the screen, we'll need a set of alphanumeric character graphics, similar to how we drew the countdown timer, but this time we need something a little more flexible. So jumping back into VS Code, let's quickly have a look at the MISC PNG image that we brought in the previous video. You may notice that we've used quite a lot of this image already, but if you focus on the middle, it contains a couple of alphanumeric character sets, along with a few other symbols, which we can use to write strings to the screen. The scores in the status bar use the left set, so the first task today will be to bring these into our code. Opening up the status bar class, I'll start with both the fighters' scores. Referencing the original game, we only really need 3 characters for this, the letter P and the numbers 1 and 2. Wow, I feel like I'm on an episode of Sesame Street. Anyway, just like before, we'll have to add these frame details into our frames map object. Although again, as I already have these defined elsewhere, I'll copy and paste them here to save on time. Replicating what we did before for the frame name, we'll use a prefix followed by the character itself. In this instance, I'm using score. And before we move on, I'll add a quick comment above each, like we've done previously to describe what each are. Next we'll add a stub function to house our draw calls for the score section, which funnily enough I'm going to call draw scores. This function will naturally require the context object, like the other draw functions. We'll then call this new draw function within the main draw function, passing on the context object. Let's put it at the top of the call list, as we want this to be the first thing to be drawn to the screen. Also, while we're at it, I'll just move our local draw frame function down with our other draw functions to keep things tidy. Okay, back to our draw scores function. We'll now simply draw the correct character frames in the correct positions on the screen. We'll start with the P1 and P2 labels first. For the actual score values themselves, let's create another function called drawScore to house our score drawing logic. This function will have a further two parameters, the score value itself and an X position presenting where it will be drawn. And just like before, we'll call this stub function within the drawScores function, passing on the necessary arguments. I found that Street Fighter tends to start every new player with a score value of 1, so let's copy that here too and hardcode that value for now. Again, we'll come back to this soon, once we start to implement the global state in a future video. In regards to the drawScore function, this will take the score for each fighter and iterate over the individual characters of that value, and draw them to the screen at the designated position. For this to work, the first thing we'll need to do is to ensure that the value is actually a string, as iterating over a string is far easier than a number value in this instance. So we'll use the string constructor and pop the results into a new variable. Before we continue, let's quickly reference the original game again to see how it presents its scores on the screen, as this will help us understand a few things. The main takeaway is that the values align to the right hand side, and can be a maximum of 6 characters in length. Also, if you look a little closer, each individual character is evenly spaced out by 12 pixels. Okay, with this knowledge, we can work out the actual X position we need to use in our drawScore function. We'll take the maximum number of characters and multiply this by the character width, which will give us the total space available for the score. We'll then minus the actual length of the score string, and again multiply that by the character width. The result is an offset X buffer, which we'll need to add to the base X position, so that we have the correct starting X position. With that done, let's now iterate over the characters and draw them to the screen. We'll do this with a for loop and step through the content of the string value, based on its length. With each character, we'll draw it using the corresponding score frame, and adjust the X position based on the index, multiplied again by the character width. Finally, just like the other draw frame calls so far, we'll use a Y position of 1. Okay, let's take a step back and have a quick look in the browser for the first time in this video, and see what we've achieved up to this point. Great! The player's score labels, along with their initial scores, are displayed at the top of the screen. Nothing overly exciting at the moment, but the code we've written so far should work with any score value we pass into it, so we're all prepped for the future. We do have a gap in the middle though, which is missing the high score name and value however, so we'll get onto that next. Back in the code, let's add a new high score value to our drawScores function, as we know we can cater this quite easily with the drawScore function we just completed. I know from the original game that the default highest score value is 50,000, so we'll use that and hardcode that value in for now. Again, we'll come back to correct this in a future video. Next, we'll need a new function to draw the associated high score name string. So let's create that and call it drawScoreName to house the draw logic. This will take the context object, a name string, and an X and Y screen position coordinates. Although as you can probably expect, before we can progress any further, we'll first need to extract the remaining alphabet frames from the MISC image. So back in the constructor, I call upon my predefined list of definitions and copy them over as per usual, both for the numeric and alphabetic characters. As a result, we now have a full list of alphanumeric characters to play with in our score display. Please freeze the video if you wish to copy these. In the drawScoreName function, just like before, we'll use a for loop to iterate over the name string, but this time we don't need to adjust the starting X position. We'll just use the index from the in clause. Again, we'll just evenly space out the characters based on the character width, which we know is 12 pixels. Looking back, we probably don't need the Y position, as we know the scores all appear on the same line. So let's go ahead and remove that now. With that now complete, let's call it within our drawScores function. I'm going to use the name of Ant for now, because why not? In fact, we can actually replace all our current draw frame calls too. So let's do this, passing in P1 and P2 as the name argument. As the drawScoreName function is drawing more than just names now, let's give it a more accurate name. I'm thinking drawScoreLabel. We'll also change the name parameter too for consistency. There you go, much cleaner. Another quick check in the browser, and great! All the scores on their labels are correctly drawn at the top of the screen. Moving the focus to the stage background now, it's looking a little too static for my liking. Each stage in Street Fighter had a number of animated objects and layers in all of their backgrounds to give it some life. In terms of Ken's background, this was mostly the boat and the various onlookers that he had on board. Let's look to add these to our background next, starting with the bob emotion the boat has. which gives the perception that it's floating on the sea. So in the stage class and its constructor, let's add a new local property called boat. This will hold all the properties that we'll need to animate it. Similar to how we've done it in the past, these will include animation frame to hold the frame number, animation timer to hold a copy of the frame time, an animation delay property to hold a delay between each frame, and lastly the animation itself, which I'll set up a sequence of numbers ranging from 0 to -4. We'll explain what these numbers actually mean in due course, but let's continue on. We'll next add a new local function called updateBoat, passing on the frame time argument. Then we'll call in the main update function, which we'll finally put in use today. We'll now set up the boat animation, but before we do, we'll need a couple of more constants to help with the animation. So in the constants folder, let's add a new file called game.js. This file will house any constant values that relate to the game itself. If you remember back in the animation video, we discovered that Street Fighter 2 ran at 60 frames a second. We'll start by adding a base variable called FPS and set this to 60. Then we'll add another called frame time, which will be a calculated value of 1000 divided by this FPS variable. The value of 1000 is ultimately 1 second in milliseconds. So in summary, the game runs at 60 frames a second, and each frame has 16.6 milliseconds of time available to achieve that. So if a frame takes longer than this expected time window, it means the game will start to drop frames. In terms of our boat though, we'll be using this value to calculate if the animation delay value has exceeded a certain amount of frames based on the frame time. Back in the stage class then, we'll now set the boat's animation delay with a base value of 22. As mentioned, this is the amount of game frames of delay between each of the boat's animation frames. Let's move on to the update boat function and bring this all together, where this will hopefully be a little more clear if not so far. Just like we've done previously, we'll now check if the boat animation needs to update. We'll take the previous time property and check if this is higher than the boat's stored animation timer value plus its animation delay value, which we know is currently 22, and multiply it by the frame time constant, which we know is 16.6. This equals to a value of roughly 365. So this animation frame will have 365 milliseconds of delay. Moving on, if this time has exceeded, we'll first store the previous frame time value to the animation timer property. Then we'll increase the animation frame by 1. For those who are keeping track, this is very similar to how we've done the animation loop in the fighter class. The thing we're going to do slightly different here is that we're going to set a new animation delay value each time the boat changes frame. The original game seems to have some randomness to the animation delay, so we'll simulate it here too. We'll set it again to the base value of 22, but give it some wriggle room of 8 frames either way by using the math random function and multiplying it by 16 and minusing 8 from that. Also, like before, we don't want the animation frames to exceed the animation array length, so we'll just do a quick check here and reset it back to 0 if it has. Now that we have the boat animation set up, we can move on to drawing it. Let's create a new draw boat function above the main draw function, passing in the context as per usual. We'll then move the original draw frame call over to this function so we can update it. To make things easier for later, we'll create a new property within the boat object called position to store its x and y coordinates. With that in mind, let's also add a camera parameter to the function too. We'll then move the x and y values from the draw call and move them to this new object. Although for the y position however, we're going to apply the boat animation we've just set up. We'll take the camera's y position and add the boat's animation to it, based on its animation frame. We'll now replace the missing x and y parameters in the draw call with these new variables. And to complete, we'll add a call to this function in the main draw call, in between the two current draw frame calls, to ensure they are drawn in the right order. Another check in the browser, and the boat is bobbing up and down as expected. As you can hopefully gather, the boat's Y position is changing based on the animation array, using a random delay between each frame, which gives it a little more life. In fact, the characters on the boat seem to be lacking that life at the moment, so let's look to get them animated too. As all the people on the boat are basically just a sequence of animations, let's add a new generic class to contain this logic first. In the entities folder, we'll first create a new folder called stage, which will contain any entities and classes that relate to stages. In this new stage folder, we'll start by moving our stage class over to it. Then I'm going to create another folder called shared, which strangely will house any entities that are shared amongst all stages, not just Ken's. In this folder, we'll then create a new file called background animation, and set this up as a new class as we've done before. As mentioned, as we have numerous background animation entities on each stage, this class will contain all the logic for those, so that they are in one place. The constructor will take a few parameters to configure the entity though. We'll pass on an image reference, which will come from our stage, a frames object that will contain all the animation frame data, and then the animation details itself. Optionally, we'll also allow a start frame just in case the animation requires starting out of sequence. We'll then pass these on to the local properties within the class as we've done before, also adding the update and draw stub functions again to follow our usual entity pattern. Within the draw function, we'll then take the frame key from the animation based on the animation frame and use it to get the frame dimensions from the frame map object. Finally, passing these on to the context drawn image call. Standard stuff so far. The only difference is that we're passing on the x and y parameters onto the function, which will be controlled by the stage class. Moving on to the update function now. Again, we'll follow the same logic as we've done before for the animations in the previous classes, taking the time object and comparing it to the stored time object for the animation and delay, and then increasing its frame if the frame delay has been exceeded. As per usual too, we'll also reset the frame if it has exceeded the animation length, while updating the frame delay and timer in preparation for the next animation frame cycle. If you've been following the series, hopefully you're starting to see a trend here, as we start to fill out the entity's update and draw functions. If so, none of this code should really be unusual to you. As we've moved the stage class file, let's not forget to update the import references within the Street Fighter game class and the stage class itself. While in the stage class, let's go ahead and import the new background animation class too. Okay, let's now move on to setting up the background animations, which we know are the people on the boat cheering our fighters on. Let's add one of these to the constructor. Referencing the ship, working from left to right, means we'll start with this bollard. We'll add a new local property and create a new background animation, calling it, bollard. Why not, I guess. We'll pass on our image reference, and then from the animation and its frame data, I'll copy these across as I prepared this code earlier. But ultimately, these follow the same structure as those in the fighter entity classes. Just to quickly recap, each frame has a unique key value pair. The unique string key has an array of 4 values, which are the bounded box on the image containing the frame of animation. For example, our bald man has 3 unique frames, which are then used to map out this animation in the last array. The animation sequence contains a unique frame from the frame data and the amount of time or delay this frame will be shown for. As for all the other characters on the ship, they all follow the same process, using a unique local property name to represent them. Although rather than typing them all out, I once again have them prepared, so we'll copy them over here. Please pause the video if you wish to copy the code. Or if necessary, why not become a patron where you can gain access to the code directly. Details are in the video description. Sorry, plug over. Either way, we'll now move on to the main update function and add these new properties there, calling their individual update calls passing on the time. In the same vein, now in the update boat function, we'll call each of the entity's draw function passing on the context, and the boat's position as the base and y coordinates. Then for each, we'll offset these values to align them correctly to their actual positions on the boat image. With another check in the browser, it would seem all the characters are now animating as expected, with the exception of one, the guy to the right of our original barman character. This is because he actually doesn't seem to follow any set animation from what I could see in the original game. For this reason, we'll have to do something different from him personally. Although, there is one animation we can add first however, and this is the American flag on the other boat to the right. This too can use the background animation class we just created, so let's add that first. Back at the top of our constructor, we'll again follow the same process as the others. First copying over the predefined data for the flag local property, using the same structure as the other background animations. Then in the update function, adding the flag's update call there, forwarding on the time. For the flag's draw function, as it's attached to the sky and ocean background layer, let's do a small refactor to help with its positioning. We'll first create a new function called draw sky ocean, and in the same vein as the draw boat function, we'll pass on the context on the camera. Then we'll move the current draw frame call from the main draw function to this one, and then replace it with the call to the new function instead. Similar to the boat function, we'll create a base position value for all the other draw calls in this function too. Although, as this image only moves on the x-axis, we'll just need an x variable, which I'm calling background x. We'll then move the math.floor function and its contents over to it, and replace it with this variable. With that change, we can now add our flag's draw function to this function too, using the background x variable, while offsetting the necessary x-axis to ensure it's aligned correctly to the sky and ocean background image. Let's quickly check the browser again, and it would seem the flag is now happily flapping around in the wind on the boat in the background. Okay, to complete the background animations, let's now tackle the grey trenchcoat guy's animation. As this is a special case, we'll first add his frame data to the frame's map object instead. Then we'll add a new local property to hold its animation details, just like we did with the boat object. Adding it just above that one. Notice the absence of the animation property though, we'll be manually producing that in code this time round. So under the update boat function, let's create a new function called update grey suitman, for the lack of a better name. Here we'll repeat what we've done before, comparing the time's previous value by the entity's animation timer plus the animation delay values. As for the animation itself, we'll be flipping between 2 frames of animation which performs the guy's head bopping up and down motion, as seen here by inverting the variable with a knot. We'll be doing this on a random delay to give it some variation, similar to the boat animation above. I'm using a base value of 100 milliseconds, but with a variation of a further 900 milliseconds per frame. Finally, we'll also reset the entity's animation timer for the next cycle. Once complete, we'll add this new function to the main update function. To get this entity drawn into the canvas, we'll go back to the draw boat function and add a new draw frame call. We'll use the entity's frame string prefix of greysuit and concatenate the animation frame property to this string. As this property flips back and forth between 0 and 1, we'll need to add a 1 to it to ensure it matches our frame keys. We'll then use the boat's X and Y position as a base position, and again offset the entity to align it to the correct position on the boat image. And with that, we'll have another quick check in the browser, and the grey trenchcoat man seems to be bobbing his head along with the numerous onlookers, which is great as it means we've completed all the background animations. So let's now move on to the floor and look to add the fake but clever 3D skewing effect, as it's not really cutting the mustard at the moment in its current form. We'll add a new class file to the shared folder, next to the background animation file called skewed4. This class will take a number of parameters in its constructor to allow the class to be reusable, as I know some other stages use variants of this entity for such things as ceilings. More on this in a possible future video, but for now we'll forward on the image reference, which will be owned by the stage itself, and the box dimensions that contain the floor graphics on that image. We'll then create local properties with the same names, and pass those on. Next we'll add a draw function, which will take the usual context and camera properties, but also a Y position, so we can pass on where we want the floor to be drawn from the stage class. Inside we'll first deconstruct the source variables from the dimensions property, and pass these on to a context draw image call, using the local image property as the image source. Notice how both the X and Y destination coordinates are oddly 0 here. We'll come on to the reason for this in a second. But with this in place, let's move back to the stage class and update the code there so that it calls this new class. Let's add a new local property called floor and assign it a new instance of the skewed floor class, passing on the stage image property and the dimensions from the stage floor frames key. We'll then move down to the main draw call and replace the current draw frame call with the new floor properties draw call. I'll cut the X and Y position values and store them in memory before doing so, however. Following the usual trend, this call takes the context and camera arguments, but we'll need to pass on the original Y value of 176. With the stage class now set up to use the new skewed floor class, let's jump back to it and get the floor working as it did previously, before we started abstracting out the new code. I'm going to introduce a new context function called setTransform. We'll go into detail about what this does in a moment, but in a nutshell it works very similar to the transform function we've used previously, in that it allows us to apply transformations to any future context draw calls. Either way, it takes 6 arguments. The first 4 I'm going to be using 1, 0, 0 and 1 for now, but for the last 2 I'm going to paste in the original X and Y positions we copied earlier from the floor's original draw call, replacing the 176 with a Y parameter, as we're passing that value into the stage class anyway. And that should now get us back to where we were before we made any changes. Although if you remember our previous run-in with transformations, you know that we should really reset them back after we've finished using them, as it could cause some unwanted behaviour. So for this, I'm going to introduce 2 more new context functions to help with that. The first is the save function. This ultimately saves the context state into memory, which includes the current transform matrix. So we'll add that before any context calls in this function. Then we'll add the second, which is the restore function. This, as you can probably guess, restores the save state back into the current state, overriding any changes we've made in between. Thankfully, this includes any transformations we've set. Great stuff. Let's now check how this looks in the browser to ensure we've not broken anything. And it doesn't seem so. The floor is still being drawn as expected and moves as required using the camera. Okay, before continuing on with the code, let's take a small break and briefly explain how we'll be using the transform matrix to apply the floor effect like the original game. Until now, we've been using multiple layers of backgrounds and moving them at different speeds to create the illusion of depth. In 2D games, this is called parallel scrolling, which simulates certain distances away from the camera. In regard to the floor and ceilings, however, Street Fighter 2 used a technique that relied on how the hardware updated its screen. Graphics hardware at the time would generally follow the frame buffer, line by line to the screen, top to bottom. Knowing this, games like Street Fighter could interrupt the drawing sequence and inject small sections of code to manipulate how this line would be drawn to the screen, meaning it could horizontally offset the floor or ceiling layer on each vertical line as it was being updated, progressing down the screen. This is why the floor graphic looks more deformed on the outer edges, as it was to cater for this image manipulation. Although, as you can see from this example, once the image has been correctly adjusted on each line horizontally, the once deformed sections now appear to look correct. In essence, it's basically the same effect as parallel scrolling, in that you're updating the graphics at different speeds based on the camera's horizontal position. However, rather than it being applied to multiple whole layers or images, it's applied directly to one layer or image, and specifically line by line. Putting this all together produced a clever but fake perspective effect. Impressive stuff. As for our version though, we don't have access to such hardware trickery on the web, but luckily for us, we can definitely simulate it with a similar 2D transformation effect known as skewing. Skewing does exactly what we've just described by applying a slant to an image. You may be familiar with this already, to be fair, as CCS also has a skew function that can be applied to the transform property, but that's a topic for another video. In terms of the Canvas API, we are able to perform skewing with the context transform matrix. As you've already seen, we'll be leaning on the set transform function for this, so let's quickly explain how that works too. The set transform function has 6 parameters that all control the viewport's display matrix. These allow you to perform a few different transformation effects, which funnily enough one of those is skewing. Parameters 1 and 4 control scaling, while 5 and 6 control positioning, which we've just used. And specifically for the floor, 2 and 3 allow us to manipulate the vertical and horizontal skewing positions respectively. Although to be fair, for the floor, we're only interested in the horizontal value. Applying a negative value here will make the drawing function skew to the left, whereas applying a positive value will make them skew to the right. And with all that's been said, that's all there is to it. If we apply a calculation based on the camera's X position to this value, this should give us the same effect as the original game. So let's jump back into the code and apply what we've learnt. In the skewed floor class, we'll change the parameters of the skewing arguments from 0 to the values I found to work quite well. Starting with the X skewing position, the third parameter, we'll use the base value of -5.15 and minus the camera's X position, which itself deducts the stage width and stage padding values. To complete, we'll then divide this value by 112. In summary, this gives us a value between -1.7 and 1.7 depending on the camera's X position. Then for the transform's X position, the fourth parameter, we'll replace what we have and start with the base value of 32 and deduct the camera's X position, which we'll divide by 1.55. And that's it. You should now have the transform skewing as required for the floor. So let's take another look in the browser and see the results. With the transform now being affected by the camera's X position, the floor seems to be skewing correctly in relation to the fighter's movement. I'll be honest here though, after many hours of tweaking these values, they might not be 100% authentic to the original game, but as you can see, the values are certainly good enough to at least prove its concept. We may come back to this in a later video to refine what we have. In fact, why not experiment with these values yourself and report back if you find better alternatives. Although, before we move on, if you look closely at the bottom of the screen, we're incorrectly skewing the vertical section of the floor, so let's fix that first. Back in the stage class, we'll first deduct 16 pixels from the floor's height in the dimensions array, as this is the actual height of the floor we want to skew. Let's then reuse the old frame key, stage floor, as we currently have no use for it, and rename it to stage floor bottom instead. We'll update its Y and height position values, just to cover this bottom section of the floor. Then at the bottom of the class, we'll create another draw function, as we'll need to draw this new bottom frame with the skewed floor. We'll call it draw floor and move the current skewed floor draw call over to it. And yes, adding a call to this new function in its place. Then finally, we'll add a new draw frame call to the new stage floor bottom frame we just set up. We'll use the stage padding as a base X position while minusing the camera's X position and using 232 as the base Y position. Notice how we've multiplied the camera's X position by a value greater than 1 here, which means it will move slightly faster than the camera, again solidifying the illusion of depth. Another quick check in the browser, and the bottom section of the floor now seems to be corrected, and moving in relation to the new skewing effect. Okay, now that we have this floor updating as expected, let's move on to populating it with the missing background objects, starting with the bollards nearest to the boat. In the frame's map object, we'll first add the bollard keys and their frame dimensions. The bollards come in 2 sizes, which I'm calling small and large, but we'll focus on the small ones at the moment, as they sit on the floor behind the player. Then, just like before, we'll move down to the bottom of the class and create a new function called draw small bollards. As we'll be drawing 2 of these small bollards, we'll set up some temporary variables so we can use them for both. The camera's X position first, with its camera speed modifier of 1.54, and then a Y position of 166. We'll then draw both of these small bollards on screen using the draw frame function, using the small bollard frame key and the temporary variables we've just created. And then finally add the call to this function within the main draw function. Checking the browser shows that we now have 2 bollards behind the fighters, and they move in line with the camera's movement. Great! So we now just have one more object that's drawn behind the fighters to add, and that's the barrels and boxes that appear to the right of the stage. We'll follow the exact same process again with the barrels background object. We'll first add the new frame key, barrels, and its dimensions to the frame's map object, and then move down to the main draw call and add a new draw frame call using it. As this object moves at the same speed as the camera, this object does not require any modifier however. And honestly, that's all we need for this one right now. So again, just to ensure everything works as expected, we'll check the browser to see the results. Moving to the right, we can see the barrels and boxes now correctly slide in when the camera is at the furthest right of the stage. Okay, with all the background objects now in place, the last thing we'll add in today's video will be the foreground objects. These objects are still background objects, but actually get drawn last, and in front of the fighters. A number of the stages have these type of objects, but in regards to Ken's stage, these are yet another set of bollards. So let's jump back into the code and make the necessary adjustments to accommodate these. For our stages moving forward, I like to break tradition and move away from just one main draw function. As we now know, stages have multiple drawing layers, those that happen before and behind the fighters, and those that happen after them, and therefore in front of them. With that in mind, we'll start by creating a new function called draw foreground to house these new draw calls. Likewise, we'll now rename the current draw function to draw background instead. With that change, this now means the stage class no longer follows the standard entity interface, and for that reason can no longer be part of the main entity array within the Street Fighter class, as we've removed the main draw function. So back in the constructor of the Street Fighter class, we'll create a new local property called stage, and create a new instance of the stage class, meaning we can remove the previous instance from within the entities array. Then within the update function, just like the camera property in the previous video, we'll call the stage's update function here individually instead, passing on the same arguments. Similarly in the draw function, we'll call the stage's newly renamed function draw background before the entity for loop, meaning the stage and all of its background elements will be drawn before any of the entities within its array. We'll then add a call to the draw foreground function after the for loop to ensure this layer has been drawn after any of the entities. And with those changes, we should be ready to add the foreground elements to the draw foreground function. So back in the stage classes constructor, we've already got the frame data for the large bollard, so we can go ahead and add the draw frame calls to the draw foreground function. But before we do, we'll first set up some temporary variables like we did in the draw small bollards function earlier, as we'll again be drawing multiple bollards here. We'll start with the midpoint variable, which uses the stage midpoint and the stage padding constant values to get the middle of the stage. Then, just like before, we'll get the adjusted camera's X and Y positions using an X speed modifier of 0.958 and a Y position of 200. We'll then make 2 calls to the draw frame function, using the bollard large frame key and these temporary coordinate values, adjusting 147 as a base X position on each side of the midpoint. And if we check the browser, we should now have a complete background that replicates Ken's stage from the original game, with both the background and foreground bollards working as expected. We've made some great progress here, so I think that's where we'll call it quits for today's video. As per usual though, there's a few little refactors I'd like to make before we actually do that. The first thing we want to do is to move the code we just wrote for the large bollards over to its own function. So let's create a draw large bollards function and do just that, and then make a call to this one from the draw foreground function. And just to keep things tidy, we'll make sure it sits next to the small bollards function. Next, as we've been making changes to our entities array, I'd like to do something similar for the overlays. The reason for this will become more apparent in the future videos, but ultimately overlays should be drawn last, over the top of everything else, so it would be smart to have a separate draw list for those. So in the Street Fighter game class, we'll add a new local property called overlays, and move the status bar and FPS counter instances over to it. Then in the update function, we'll copy and reuse the entity for loop and make the necessary changes for the new overlays array, looping over its list. We'll do exactly the same within our draw function too, looping over the array, but this time calling the overlays draw function instead. A small check in the browser, and yep, huzzah, we've not broken anything. Okay, let's continue. The next change on the list will be to rename the stage class to Ken stage, not forgetting to update the class name within the file along with it. This makes it more obvious what the class is for, and furthermore allows us to add the stages for other fighters more easily, if we ever wanted to. Although, as we're renaming the file, we'll have to ensure we update any input references too where necessary. Luckily this is only in the Street Fighter game class, both in the import and in the constructor. Similarly, we'll do some more file changes with the next refactor. I'm going to add a new folder called Engine and move the input handler and camera files over to this. This change is a general house cleaning exercise to keep the generic engine code away from the actual Street Fighter game code. If we get time, we'll look to flesh out the engine code somewhat in the future videos. Either way, with that move done, we'll again need to update any input references we've now broken. These include the Street Fighter game class, the fighter class, the camera class, and the input handler module. And continuing the theme, for the last change today, we'll move the FPS counter class over to the overlays folder. Again, ensuring we update any input references, which luckily for us, VS Code was smart enough to do this for us this time. So for the last time today, we'll have another quick check in the browser, just to ensure we haven't broken anything. And it seems everything is still working as it should. Okay, and that's what I think we'll call it quits for today. So let's quickly recap what we've completed in this video. We now have Ken's stage pretty much complete at this point. We've added all the background animations, which include the boat bobbing up and down on the water, along with its number of characters to give it some life, but also the flag on the boat in the distance. We've added the skewing effect on the floor to give it the infamous 3D feel, while adding the various objects that sit atop it, furthermore solidifying the feel of depth as we scroll back and forth. And finally, we've added the initial scores along the top of the screen, which we'll come back to in a future video once we apply some global state. Hopefully you'll agree, the game looks pretty authentic at this point, but we're missing the main ingredient to actually make this a Street Fighter game, the actual fighting. Not to worry, we'll finally start tackling some of this in the next video, where we'll add the basic attacking moves and apply the hit and attack collision boxes. So yes, it'll be yet another big one. But first things first, let's sign off. Apologies for the delay between this video and the previous one. As mentioned in the previous video, I'm finding these are taking longer to complete at the moment, due to exploring the game's more complex topics now, and with my delayed summer break this past month, they have both unfortunately contributed to the delay of this video. So the release schedule will still be a little erratic for the next few parts, as I attempt to get back into the code and finish up the topics I have planned for future videos. I regularly drop update messages on my Patreon page if you'd like to keep up with the latest news, which are all free by the way. Although a vlog will probably drop here too at some point over the next month, just to summarise visually where we're at. And finally, thanks again for all the support so far. You don't know how appreciated I am, both with the Patreon page and the new subscribers to this channel, especially while I've been away. Honestly, it's been a shock. And as you've probably already noticed, my Patreon supporters will now appear on these end credits. And I think that's all for now, but as per usual though, if you've gotten this point in the video, a special acknowledgement goes out to you too. You're the special ones. Hopefully I'll see you in the next one. And out.